Hello, and welcome to the IEEE Spectrum Online presentation, 5G Hybrid Beamforming Design. I'm Dexter Johnson, and I will be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items. For those of you using Chrome and Edge browsers, if you have Flash blocked, please click on the play button on the media player, and that will ensure that you're getting the slides. For those of you who want to know if this session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours. And once the archived webinar is available, a notification email will be sent to all the registrants, and that includes all of you here today. Also, we encourage questions, and I hope we'll have time for several, which we'll take at the end of our presentation. As your questions occur to you, please type them in the box provided on your computer screen on the right-hand side and hit the submit button. You don't have to wait until the end of the presentation to begin submitting questions. If you're looking for the PDH certificate code, this will be given in a slide at the end of the presentation. As you look over the screen, you should also see buttons that allow you to enlarge the slides if you so desire. About volume control, if you're listening to the audio over your computer speakers, you may need to adjust the volume on your computer. At the bottom of the slide in front of you are a couple of additional widgets that will improve your viewing experience, including the green resource page with today's presentation and a link to the PDH certificate code form. Now I would like to introduce our presenter for today, Dr. Houman Zarankoub, Senior Wireless Product Manager for MathWorks. Houman specializes in wireless communications and signal processing at MathWorks. Previously, he worked as a senior research scientist at Nortel Networks, contributing to global standardization projects on mobile and voice processing technologies. He's a book author and holds multiple patents. Houman received his Bachelor of Science in Electrical Engineering from McGill University and a Master of Science and a PhD from the University of Quebec in Canada. And with that, Houman, I'll pass it over to you.
Thank you, Dexter. Thank you very much, everyone, for attending this talk. We are very grateful to IEEE Spectrum for hosting this session. And as Dexter mentioned, the topic is 5G hybrid beamforming design. So let's go over the agenda of the talk today. I have organized this talk into essentially 7 sections, as you can see. Introduction puts the talk into perspective, and then we go through essentially 5 stages or elements of the 5G high beamforming design that you see here. And finally, I summarize and provide areas for further learning and research. On this slide, you see the MathWorks or MATLAB capabilities for wireless communication that we have provided here. Of course, as you can imagine, we have mobile connectivity standard product set, MATLAB functions for different various standards. Today's talk is mostly on the joint design of RF and baseband and antenna simulations and channel modeling and propagation. You will appreciate that if you're interested in essentially modeling and simulating wireless systems end-to-end. And of course, we have a bunch of capabilities in terms of testing live with MATLAB and essentially generating HTML and C++ code for implementing it, but that's not part of the talk today. So let's look at the introductory remarks and go from there. Of course, 5G is being deployed everywhere in the world. You know that the 5G standard, supersedes the 4G or LTE standards. The productization took place. The standalone version was standardized in 2008, and ever since that, companies have been developing modem chips and base station and UE or handheld devices in order to support the 5G standard and develop the 5G networks. As you might imagine, every G respect to previous G, I mean 5G respect to 4G, provides essentially new use cases and applications, as well as improved performances. In terms of the nomenclature, you're all familiar with these three nomenclatures that you have here. Enhanced mobile broadband essentially means that for broadband communication between people using cell phone structure, we are going to have a one leap around the maximum throughput provided by 4G. Low latency is very important for time-critical applications like remote medicine, virtual reality, where you want to decrease the amount of latency between transmit and receive links. And massive machine-type communication, or IoT, is important for those applications where lots of devices, well beyond phones, will communicate with the wireless networks. So one standard is trying to achieve all of that. Let's see what technology enabling all this. So in terms of technical enablers, if you want to go from 4G to 5G, you need to look at the requirements. You want to have increased capacity or increased throughput to your network, right? One way to increase the capacity and throughput is to increase the bandwidth and increase the spectral efficiency, which is how much bit per second per hertz of bandwidth. So in terms of increasing bandwidth, as you may imagine, the LTE allocated a 20 megahertz bound on the bandwidth of the its available modes, 10 modes of LTE, maximum mode 20 megahertz. You could do 5 times carrier aggregation and achieve a bandwidth of 100 megahertz, but that was it. But for 5G, they're going beyond that. The kind of lowest bandwidth that you're talking about is about 50 megahertz, and using what we'll describe soon, you can get 100, 200, even 400 megahertz of bandwidth. So one of the defining features of 5G is increased bandwidth. And then if you increase the bandwidth, you need a place where a contiguous band of spectrum available for this bandwidth. And that is, fortunately or unfortunately, we have to go from our legacy mobile communication bands around 2 or 3 gigahertz, way beyond 6 gigahertz, which define the millimeter wave. The minute you do that, the minute you go to millimeter wave, the drop or attenuation in energy is so severe that you need to use MIMO techniques and multi-antenna to boost the signal, and that is essentially the way that we achieve better spectral efficiency. Of course, the flexibility is there. You want to be moving between different bandwidths and so on, so there is a new information. I'm going to talk to you about that soon. And the notion of small cells. We're going to create lots of smaller cells tuned at these frequencies to achieve all of that. So maybe you know about this. I thought to refresh your memory on that. The second, we talk about millimeter wave. One of the huge challenges become propagation, as you can imagine, not only because of the nature of free space loss of millimeter wave, but also because of the bandwidth, because of the wavelength. They are subject to all kinds of atmospheric gas and fog and so on, attenuations that becomes more severe. If you have a large bandwidth, 50, 100, 200, you are subject to multipath fading severely, so you have to take care of all the line of sight and non-line of sight, multiple paths of connectivity between the base station G node B and the UE, and then you need a scatter-rich propagation environment. The thing about the scatter propagation, we're going to use the scattering to our advantage, but then the traditional channel modeling and propagation based on MIMO channels, Rayleigh, Ricean, which assume kind of a uniform propagation through the air, will have to be replaced by kind of a ray-based optical communication, spatial communication, where you have a one-hop or two-hop reflection or refraction between the antenna array and the received signal. So that is a new set of challenges for propagation. We're going to talk about that soon. Now, I told you large antenna arrays becomes a must for millimeter wave communication, even for the regular frequencies. Now, you can choose an all-digital beamforming approach when you are doing MIMO communication. Of course, beamforming and spatial multiplexing are two modes of using MIMO techniques, the multi-antenna techniques. In beamforming, we essentially have one stream that we repeat across different spatial antennas. In spatial multiplexing, we are using multiple streams or multiple, if you like, the nomenclature of 5G, we're using multiple layers. But what they have in common is that you can actually have beamforming implemented in a way that each of those baseband IQ samples that arrive at each antenna port can underneath them be an RF chain, where each of them have their own RF amplifiers and so on. That becomes complex and power hungry. So hybrid structures, which they divide an antenna array into sub-arrays and divide the beamforming approach or the MIMO approach into digital approach, hybrid with analog approaches, will actually save you a lot of power and complexity, because the sub-arrays are subject to RF chains, not every single antenna element. And that is the reason why we're talking about hybrid beamforming as a compromise between performance and complexity and power usage. This, what I'm showing you, is essentially one way of describing the whole overall hybrid beamforming architecture, where you have baseband signals generated at G node B or UE, and we have the partitioning of the MIMO transmission scheme into digital and RF beamforming or MIMO. We had a MIMO channel to map the transmitted array to a received array, and we have a hybrid structure, the partitioning between digital and analog or RF on the receiver or combined side, and then we go and get from that combiner all the modulation data, and we go all the way to receiver operations. And the key is that in the middle, the MIMO channel, if we get knowledge from MIMO channel, we can actually compute all the weights, all those beamforming weights that have to be applied in the digital beamforming to each antenna port, and in the analog beamforming as phase shifts. We can derive them in the submodule, which actually derives them from MIMO channel characteristics. So I'm showing you a Simulink diagram, not MATLAB, but a Simulink diagram, where the baseband processing, the digital and RF beamforming, the channel modeling are all implemented in the same environment. Why do I show Simulink? Because, as you can imagine, RF is implemented not in the digital domain or simulated. It's essentially continuous time or kind of analog domain processing, whereas the baseband is discrete time. Simulink is a MathWorks product and an environment and platform for modeling and simulation, which both can run analog and digital, discrete time and continuous time signal processing. So if you want to combine the RF and digital design, Simulink environment provides you that information. I'm going to go now and break it down for you in terms of how we do all of this, architecture and what is involved with that. So you are looking at the system-level design consideration for a hybrid beamforming architecture. This is for MIMO and beamforming and spatial multiplexing 5G systems. As you can see, not only you have to deal with the baseband waveforms and the stuff that comes from a modem chip on transmit side and receive side, you have to worry about the analog and digital front end and beamforming and all kinds of stuff. So you are designing your RF and digital designs together. So what we're going to go look at today is we start from the left and go into right. We're going to see what kind of capabilities we have in MathWorks to help you generate a representative 5G waveform that you can use as an input to your design. Of course, a waveform is data. It could be images, it could be voice, it could be financial data, it could be anything. These are captured using source coding as digital signals, as bits, and then the corresponding 5G physical layer signal processing takes those bits and modulates them into baseband signals. So we're going to talk about that, how these signals get generated. Of course, you have to go in a MIMO OFDM system that we're going to talk about. You have to eventually have an array of antennas that transmit the signal from transmitter to receiver. And prior to that, you have RF and digital components that has to be discussed. So we're going to talk about the designing of an antenna array and antennas in MATLAB. We're going to talk about how channel modeling is needed for modeling and simulation of these systems. You can either create a baseband signal, RF signal, and actually using RF instruments and software-defined radios transmit over the air, or you can model that, model all the imperfections and distortions that channel add to a digital and analog signal. And we have lots of channel modeling which takes care of that for you. As I mentioned, if you know the nature of the channel, we can use that to design precoders and combiners as essentially matrix operator that map different segments of a beamforming sections one after another, and you can apply this spatial multiplexing approach to the MIMO OFDM system that's 5G like that. Then you can intelligently partition your design into baseband, digital, and RF components to save on energy and complexity. And then we are dealing with large bandwidths and maintaining linearity on that range of signals becomes a problem. So I'm going to talk about the specifying RF front end that allows you to do that. All of these segments here I'm going to discuss. We have a corresponding functionality in MATLAB and Simulink and our products to enable you to do this whole system level structure easier and faster. Let's go with the first things first, 5G waveform generation. You may be aware that 5G, like 4G, they're both based on a MIMO OFDM system. They all use OFDM as the transmission technology and definitely a use of multi-antenna techniques. And as you can imagine, if you're talking about OFDM as a basis of transmission, what OFDM does, it regards your transmitted signal as multiple tones or multiple subcarriers. Essentially takes IFFT of digital samples at a subcarrier spacing or the resolution between frequencies that are represented in signal. So that subcarrier spacing in 4G was a simple parameter of 15 kilohertz for urban areas and half of that for rural areas. In 5G, subcarrier spacing or the resolution in the frequency domain is a parameter. As you can see here, we allow 15 kilohertz like 4G, but also 2 to the power of m multiples of 15 kilohertz. But it has to be to the power of m to be efficient. So we allow 30, 60, 120, and 240 subcarrier spacing. Imagine, just by allowing larger subcarrier spacing, just by allowing that, you can double, quadruple, and so on your bandwidth, because the same data going over subcarriers that are larger essentially takes you over a larger bandwidth. But because of the time frequency duality, if you're using a 15 kilohertz subcarrier spacing, the numerology that we're talking about is that we define 1 millisecond time span of transmission of a 15 kilohertz subcarrier spacing as a slot. This is because subframe in 4G doesn't call it slot. The minute you go from 15 to 30, the slot divides by half. So shorter time span, larger subcarrier spacing, and so on. So this is one of the characterizing features of 5G, is the flexibility of choosing your subcarrier spacing, your resolution, the frequency domain, and the corresponding resolution in the time domain, which enables you to have flexibility in scheduling for multiple users. Now, when you have different subcarrier spacing, there's a terminology involved in 5G called bandwidth parts. So we divide the carrier bandwidth, all the bandwidths available for different users in the carrier, into bandwidth parts. Each bandwidth part is associated with a specific subcarrier spacing. Now, you need to know about the 5G basis of transmission, which is OFDM, that is operating on the resource grid, which is flexible to be able to do 5G waveform generation. I want to talk to you about the 5G Toolbox. I am very proud of this product. It's one of our products that was introduced in 2018 as the MathWorks standard-based product modeling and simulating and verifying 5G communication systems. So the standard was released in June of 2018, and we had this product as of September of 2018. Now we are in 2020. The next release of MATLAB is going to be quite soon, in release 2020A. You know, in MathWorks we have A releases and B releases. And ever since that first release of 18B, which is in September, we have updated the 5G Toolbox. And 5G Toolbox can enable you to generate waveforms that feature mixed numerology, meaning mixed set of subcarrier spacing and the corresponding time domain signals. Multiple bandwidth parts can be overlapping or non-overlapping, meaning you can assign to different users different portion of bandwidth as required by the standard. Multiple PD, SCH, or PUSCH, these are terminology and they're defined right now. So physical downlink shared channel, that's the user data, your voice, your video, your text that is modulated and transformed into OFDM signal for different users. They all fit the same resource grid and are subject to same transmissions. For downlink and physical uplink shared channels, which means that we support both uplink and downlink waveform generation with all of its channels and signals and all the required stuff. One of the important things about 5G that most people who are deploying 5G are worried with right now is how do you connect to network. 5G has a synchronization signal burst, a set of documents and specifications, which allows the UE to essentially connect to the best G node B, and it's fully parameterizable. We provide all of that. So when you get the 5G Toolbox, you get a complete set of physical layer signal processing specification for 5G systems. Not only the 5G standard provides you with the full protocol layer, physical layer, signal processing chain, it also comes with standardized tests. So we have the 5G NR test modules and FRC, and these are explicitly described in 38.104 or 114 documents that are designed for testing. And when you open MATLAB and you open 5G Toolbox and you open our documentation, you can actually see how easily we just allow you to go through that and look at a one-to-one mapping between the standard body, the different test module specifications, and what we have in MATLAB as MATLAB code for you for that. So if you have test module 101, which is FR1, which means the frequency range 1, sub-millimeter wave, as well as FR2, which is here. And so we have FR1, FR2. FR1 is the sub-millimeter wave below 6 gigahertz. FR2 is above 6 gigahertz. So whatever test module that is provided by the standard body in those documents, our engineers have taken that and programmed it into MATLAB code for you. All you have to do is pick that, and you will see exactly how that waveform is generated. Not only you pick and generate the waveform, every function you see here underneath the MATLAB function that generates a waveform is open, editable, customizable MATLAB code. So if you want to know exactly what happens to your bits of data from video, image, voice, step by step, from forward error correction using LPC code or polar code for control channels, then to modulation mappers and the precoding and resource grid with all the DMRS and SRS and everything you want to know is open MATLAB code. You get in there and you understand exactly how a 5G waveform is generated. That's for people who are very comfortable with programming MATLAB. What if I am not a proficient MATLAB programmer? Do you have a way for us to generate a waveform, interactively? And the answer is yes. I invite all of you to get to learn in MATLAB. There is a tab called App. There's a lot of useful apps in MATLAB. So if you're familiar with MATLAB, our main product, we have a MATLAB environment, an editor where you can compose and edit and run your programs. There's a section called App. You open the app and you see this Wireless Waveform Generator App. You click on that, a window like this shows up in MATLAB. This is essentially an app which allows you to select different wireless standard types. In the release 20A, which is going to be soon, it's already out as a pre-release, we will have 5G. But previous to that, we have wireless LAN, Wi-Fi, we have Bluetooth, we have OFDM, we have GPSK, we have all kinds of other things. So all you have to do is select your standard, your waveform. A panel will appear with all the wonderful parameters. You can set standard-based parameters, and all you have to do is click on Generate button, and we will show you the IQ samples in time domain, the frequency data representation, and the resource grid of those things. We can show more. We can show the constellation and so on. You can add impairments if you want to add phase noise, carrier noise, AWGN, additive Watt Gaussian noise. If you want to introduce IQ imbalance, you can do it right here and make your transmitted signal more realistic. And there's a wonderful export button. You click on that, and every line of MATLAB code that generated that corresponding 5G or LTE or wireless LAN waveform will show up as a MATLAB code. So you can take a MATLAB code and run a for loop around it or while loop and test multiple of these parameters for a large-scale testing of your devices. That's a very wonderful feature we have added here in our presentation. Next, so you generate the baseband waveforms. What do you do with it next? Now, for a 5G hybrid beamforming or beamforming MIMO transmission, MIMO channels are necessary for modeling those scenarios. And the way that MIMO channel is used, it's sometimes, especially with millimeter wave, you want to have a kind of a very directed communication between your transmitter and the receiver. And you want to use techniques like ray tracing and so on to see what is it. Is there a line of sight? Is there a one-hop reflection that I can find? Because when you use MIMO and you use beamforming, then you add the directivity pattern of antenna, And the way 5G is describing things, you may want to end up with a very narrow beam that's communicated between a transmitter and the receiver. And then the traditional channel modeling, which assumes transmission in all directions, have to give way to a scatter-based communication. We have all of that channel modeling capabilities for you in our tools. First of all, the 5G standard comes with the 5G channel model described in Technical Report 38.901. And there are two flavors of channel models. TDL, which essentially is more toward the non-narrow beam width transmissions, and for it's the continuation of the 4G channel modeling based on MIMO correlation, the Doppler shift, and so on. But the CDL profile of channel models is a spatial channel model, which allows you to specify the geometry of your antenna patterns and panels, and in each panel, how many antenna ports, and so on. And that can lead to a special channel modeling where the transmission is more directed and more based on reflecting of known scattering positions. Not only we have the 5G channel models, which supports from 500 kilohertz all the way to 77 gigahertz, all those spatial channel models. We also have other channel models in our tools, like Communication Toolbox, Phased Array System Toolbox, such as free space path loss, which is the basics of how different frequencies respond to distances in terms of their attenuation. RF attenuation based on gas, atmospheric gases, and fog and clouds, and traditional MIMO and Wiener-type fading channel models and scattering channel models. With all these channel models, you can actually guess or estimate the distortion and the profile of impairments that added to the signal as it's received at the receiver. Now, when you talking about a 5G, talking about the MIMO OFDM, and the MIMO OFDM works like this. We may need to do what's known as channel sounding. We have to understand the channel profile in the TDD or FDD profile. And in the TDD, the channel is shared between transmitter and receiver, just different use in time. In FDD, there are just two different channels, so you have to actually provide feedback between one or the other. Now, in channel sounding, we produce preambles at transmitter, we send it to a channel model, and using the OFDM structure of the 5G, we actually use channel estimation, and we have the MIMO channel estimate at different frequencies, different times, right? Now, that channel model at different subcarriers, different times, is expressed as a channel matrix. Every matrix can be diagonalized or decomposed using singular value decomposition. So you have this, if you like, V times D times U prime, which is the classical SVD, precoding matrix, and a combiner matrix U and V prime, and diagonal in the middle. So many times in a real system, if you do it in a theoretical way, you have to use channel sounding to compose and find the best precoder or the best channel matrix that works for the channel model in question. Then after you have that, this is the traditional transmit, channel modeling, receive data flow, and you take that V or the precoding matrix and you use it to precode the data before you transmit, and you direct it toward the area you want, and then you will see that after channel estimation and equalization, you use the same U prime, or and that is the one that's communicated between the two, and then you use for decomposition. So there is a channel sounding followed by the actual operations needed in these MIMO OFDM systems. Now, in practical approach, in 5G systems, it is very difficult to actually compute the channel estimate and find the SVD for everything. So when we do the channel sounding, the CSIRS is computed at the UE, and then that information, the channel information, is reported back to base station, and the base station uses a code book of available best matches to find the precoding. So there are practical approaches that mimic the same theoretical background, but with much less complexity. So you have taken care of the baseband signal, you have taken care of the channel modeling in the middle. How about antenna array designs? So Antenna Toolbox is the MathWorks toolbox that's been available for about 4 or 5 years that has multiple use cases for you to design a right beamforming or high beamforming or MIMO system. They provide antenna element and array design. So not only we let you design in MATLAB each antenna element, but you can space them and produce the antenna array. Furthermore, we allow you to visualize and analyze the antenna design that you have done by yourself, or you use our systems to do it. And then we superimpose that information onto maps, meaning this is a new capability called RF propagation, where you can visualize and analyze the effect of putting transmitters at latitude, longitude known and elevation known, and kind of see and visualize the area of coverage, the SINR, the received power. These are new things I'm going to show you in a second. So when you are dealing with antenna and antenna array design, not only you want to design an antenna element that resonates at a frequency, in this case I'm using a 28 gigahertz millimeter wave frequency. You can design one antenna element that resonates with that. You space them and you minimize the coupling and grading lobes and all that stuff, and you come up with the antenna pattern and directivity and all that stuff for the array. And guess what? I want to talk to you about 2 apps. Again, go to MATLAB, go to apps, and open the antenna designer. Design one single antenna element in MATLAB. Again, you design it interactively using the app. You click a button, export, and you will see the MATLAB code line by line that does the same work. So we have high-level specifications here with polarization and so on and so forth. We have a library of different kind of antennas, microstrip, bipole, this and that. You can choose from that. Not only that, we have also backing structures. What is the dielectric used to back this thing? What's the design frequency? And after you click on design, they give you all kinds of antenna analysis in terms of far field, near field, all kinds of stuff that you can need to design your antenna. Then, when your antenna element is designed, then you open another app called Antenna Array Designer. Of course, if you're comfortable with MATLAB, you can do it all in MATLAB using command line. But I'm telling you, if you are not even that comfortable with MATLAB, you can start with our apps. Even a 5G waveform generation with apps, wireless LAN with apps, antenna element design with apps, and this antenna array designer with apps. So you specify the geometry and spacing between these antenna elements, lambda 2, and so on and so forth. You provide the embedded element options, what elements are used, far field radiation patterns, directivity, S parameters, all that stuff, and you can just analyze everything right in MATLAB. Now, when you have it, you even can assume that that antenna array is ready to be deployed. Look, here I've taken the famous Washington Monument, right? With obelisks in Washington, D.C. And I put the antenna on top of that. So I know the lat and long of that place is the actual image that MATLAB will show you, and the elevation of that monument. So I created a wonderful multi-directional, antenna element array here, and you can actually find the location of your receivers and digitally optimize the transmission such that each of these receivers will be at the at the highest directivity of your stuff. So all of that can be done in MATLAB. So, and the syntax is very simple. For providing a transmitter, you just say TX site in MATLAB, and for receiver, you say RX site. And then you provide the lat and long of each of them, the latitude and longitude, and you can superimpose on the map, and you can actually visualize how your outdoor propagation transmission will look like. Not only you can do different transmit and receive, you can actually compose the typical 19 node cellular structure with different sectors using the antenna arrays you just designed, and you can actually apply way beyond free space loss. You can add urban microcell and macrocell scenarios here, and even rain propagation models. All of that are one click away from MATLAB. Look at this. Now here is where I am visualizing an urban channel link analysis and using ray tracing. So this is essentially downtown, I think it's downtown Hong Kong or Cologne. And you put the transmitter here, you put the receiver here, and other places, and then the MATLAB is aware of the location. The map we use makes MATLAB aware of the location of all the surfaces, all the elevations, and MATLAB will use ray tracing to find the right one hop or one reflection path between transmitter and every receiver. You see here the TX site and RX site to specify the thing, and one function, ray trace, is used to find between TX and RX all possible ray tracing based connectivities that then you can superimpose on it the directive antenna and design your systems. So I wonder if you agree with me that the way we enter the world of antenna and antenna array design and visualizing and analyzing it in MATLAB is way beyond when I was in college or when I was working before MathWorks. We have done a lot of work in this area to make the task of visualizing, analyzing, and simulating antenna arrays used in 5G beamforming easier for you. Let's talk about the hybrid beamforming. It's essentially beamforming, which is a part of the food groups for MIMO systems in 5G, done in two stages. You have an RF beamforming, which doesn't use those amplifiers and so on. It uses phase shifters in the RF front end, and digital beamforming, which has digital filtering and all those power amplifiers and stuff like that, and applied to the baseband signal. Now, this is I know this is a kind of a very busy slide, but essentially the number of streams used in spatial multiplexing in MIMO OFDM signal, the number of layers is the input to the system. You have to map that to the number of RF chains. That's the NTRF, number of RF chains in TX side, in transmit side. Then you have to map that to the number of transmitted antenna ports. So you see we have these precoders or matrices that take this number NS and map it to an NTRF or the TX RF chains and NT. So you have to find analog and digital precoders and combiners based on your knowledge of the H, or the channel that connects the NT MIMO transmit size to the NR MIMO receive size. And I'm showing you how that's done. We're using the sub-array approach. Instead of having a single amplifier RF chain for every single antenna, which is all digital beamforming, we not use that. We use sub-arrays. We apply digital beamforming in this direction, and analog beamforming in the other direction. So you see this system of transmit high beamforming is divided into transmit array digital, and this is where all those V or U prime, those precoded matrices are essentially estimated and applied from the channel matrix. And then we open the RF phase shifter chains in order to implement the RF beamforming technique. So you see the azimuth is kind of digital beamforming. The elevation is done using RF beamforming using phase shifters. And when you open the RF phase shifter, you see that there is essentially a mapping between Simulink data comes from digital domain. We map it to RF domain, and we use phase shifters, and those weights of phase shifters are included in the computation from channel matrix, and but there is no amplification on it. The phase shifters are on the unit circle, so we have unity power, and then we add them up, and from the antenna array, all the S parameters, we include that and create the RF beamformers. Now, all the elements of RF is a place where you can add thermal noise, phase noise, image detection, all those nonlinearities and distortions you can include in your RF chain and achieve a realistic implementation of your high beamformers and explore trade-offs in your design. Now, after the MIMO channel is in play, you have the RF receiver chain, and that is where different combiner matrices are in action, and we will take that and do the combining in the RF domain and digital domain and go to the receiver, and of course, our digital conversion AGC, all the classical RF processing receiver chains. So all of that is available in this one Simulink model. And even the input, the baseband signal comes from 5G Toolbox transmitter, that 5G NRTM I showed you. So we call a MATLAB function here in Simulink. We generate the baseband signal, goes through digital and RF beamforming hybrid here, goes through matrix and gets combined here, and then we go through the 5G receiver. We have 5G Toolbox to go back to bits and close the loop here. Now, it's all good and nice, but the RF chain has to be designed, right? So where do I start composing those RF elements, not the baseband? Baseband is very well covered by 5G Toolbox and LTE and Wireless LAN Toolbox. The baseband signals that takes the bits all the way to baseband, IQ samples. If I am doing analog beamforming, how do I compose those things? We recommend that you open another app called RF Budget Analyzer, because this RF Budget Analyzer enables you to quickly implement an RF chain right in MATLAB. So you get the nice RF filters and low-noise amplifiers and the mixers and IF amplifier or power amplifiers and bunch of other blocks from RF Budget Analyzer, RF Toolbox, and Blockset. You specify the power, noise, intermodulation parameters right there, impedance mismatches. So everything you need to know about RF design is at your fingertips, and you cascade these things, and you see in a cascaded form what is your RF budget available to this. So this is the app that you're talking about here. And in detail, you specify the components, you specify the different plotting and measurements you can do, and then you export with one button. You export this design into a Simulink model, and that is the basis of your RF chain in your high beamformer. Not only we give you the Simulink model, we give you the measurements of all that effect of RF into one Simulink model that calls that system. So that the design of RF chain is actually very, very easy. So for high bandwidth, we are dealing with the problem of nonlinearity. Maintaining a linear power amplifier profile across the range and across the frequency is very difficult. Power amplifiers will drift at higher input levels and provide everything will be destroyed because you have harmonics, you have all kinds of nonlinearity effects. So no design that requires large bandwidth is complete without you taking your power amplifiers and trying to correct for the nonlinearity with your digital pre-distortion. So you see the system here that we have a power amplifier here in your chain, and we use a feedback and estimate based on the power amplifier measurements what should be the coefficients of the polynomial that kind of corrects the power amplification. So the workflow in MATLAB is very easy. You get the IQ sample time domain wideband signals from your power amplifier into that from MATLAB, and then you use a lookup table to fit this polynomial, this Volterra type polynomial, and this matrix of A with the data that you have. And there are multiple polynomial fits algorithm in MATLAB. You see the one line here. It implements this exact algorithm with 5 lines of MATLAB code for implementing the TPD. Just to summarize what I talked to you about, we went through all the elements for which in MathWorks and in MATLAB and Simulink we have functionality to enable you to design a complete hybrid beamforming system. Everything can be explored on MathWorks.com. Our documentation is all open, available to everybody. And I have put together a solution page, mathworks.com/solution/wireless communication, which goes through all kinds of solutions for different applications beyond hybrid beamforming. But if you are focused on hybrid beamforming, we have on mathworks.com multiple examples and reference designs of introduction to hybrid beamforming, MIMO with QSB and HBPS algorithms. These are the kind of a sparse matrix approach, massive MIMO beamforming, and millimeter wave transmission considerations. If you're interested in 5G Toolbox to give you the 5G waveform generation and receiver, all you have to do is go to mathworks.com/product/5G. And there's a video there for short description. My friend has also created an 11 videos, 11 component or 11 clip video series are called 5G Explained. Not only in this video series, we don't talk about what we have in MathWorks for 5G. In 11 sections, we describe for you in about 10 minutes each what are the major design and components of a 5G physical layer system, from the numerology and bandwidth parts to channel estimation to connectivity to synchronization block. We have 11 versions, and they all can be accessed using mathworks.com/videos/series/5G Explained, or just go to mathworks.com/videos and look for 5G Explained. And I'm just going to summarize my session here. Using MATLAB and Simulink, as you saw, you can design antenna, RF chain, and signal processing baseband systems in a single environment, serving your 5G hybrid beamforming designs. So you can generate 5G and R waveforms and perform receiver operations. These are all open MATLAB code. You can change them, you can look at them, you can optimize them. You can design MIMO phased array, including subarrays that were used in the partitioning between analog and digital in hybrid beamforming. You can find out different techniques of intelligently partitioning your system into RF and digital domains different sizes for the RF chain, different sizes for digital chain, and you can go through all of them in MATLAB with just one parameter. And we have a bunch of MIMO channels and wireless communication systems for you to refer to. And inside MATLAB, you can explore choices and trade-offs that are involved with such a comprehensive design such as 5G hybrid beamforming. I hope I can fit all of that information into, I guess, 55 minutes or so. And I would like to hand off to my friend Dexter. And thank you for helping me to present this. Yes.
Great, Human. That was a great presentation. We have a lot of questions. Just try to go through the ones at the top of the list here. Is there a learning camp for wireless in MATLAB?
Yes. So what you mean by learning camp could be a collection of learning material, right? That's what I understand from learning camp. In that case, we have the best place to start about wireless in MATLAB is that solution page I told you about. So you go to mathworks.com/solutions, and you will see a wireless communication right there, and it leads to everything we do in wireless. And then you go to mathworks.com/videos, our webinar area, and you will see, just by putting wireless, all the relevant classes and the learning material related to wireless that you can choose from, including the 5G Explained that I told you about. So the best place to start, if your learning camp means how do I get to know about wireless in MATLAB, is our solution page I told you about, mathworks.com/solution, and our video that I told you about, mathworks.com/videos, and just look for the word wireless.
Okay, great. Let's go to the next question. Up to what BW does the DPT algorithm work?
Yeah, the performance of the DPT algorithm that we have, it depends on the algorithm specification. So the one that I showed you in this slide definitely works up to 50 megahertz. That is the first bandwidth of the 5G. But I have another webinar coming soon on mathworks.com that my friend from MathWorks will host. And we are going to focus on all the detail about this DPD algorithm and the range of bandwidth it supports. So we have chosen algorithms to show from our customers as well as what we designed here that works with a large range of bandwidths. And I hope that we can show you more in our upcoming webinar at mathworks.com.
Okay, great. Let me skip to someone else here. Can you include mutual coupling in your phased array models?
Absolutely. One of the elements of the phased array design is the mutual coupling estimation and optimization based on the spacing between the antenna array elements, and that has a lot of analysis and measurements associated with it. So if you just go to MATLAB, get the phased array toolbox I told you about, and you can talk to us, call us. We can give you, for every product that I told you about, the 5G toolbox, phased array, communication. If you don't have access to it, we can provide you with the evaluation copy for free, and you open the app, open the designer, and every app comes with plenty of documentation under every parameter. So if you want to know the mutual coupling button on that app, you will see open documentation, tell you the workflow, and tell you how you can include the mutual coupling in your design.
Okay, great. Just a reminder to everyone, these questions will be archived, and I think MATLAB will make every effort to answer those that we don't get to during this live Q&A. I just want to jump to someone who asked a lot of questions, gets to at least one of theirs. The question is the massive machine type communication, i.e. per base station, Not sure I've read that question quite right, but
could you tell me what is the name of the
well, someone from University of Freiburg. I prefer not to say their name. And the question is the massive machine communication per base station? What is massive machine communication?
So yeah, that's the question. The massive machine type communication is a feature of 5G which was not available in 4G or LTE. It means that within a range of a particular base station, G node B, we can have IoT type devices. That IoT type devices, as they become commercially available, these are devices that are not meant to be devices with a high throughput communications of multiple megabits per second. These are just devices that turn things on and off. They report from factory floor or a home to nearest the base station, different events. So each machine type communication could be narrow band and low data throughput with marginal links, meaning the receive signal is very low. But we at the base station have to be supporting many of them. So that's one part of 5 I told you about is what the standard body says as an objective that this many can be handled. Of course, this is a theoretical, not the practical range. We'll see what the practical system will support. Yes.
Okay, great. We'll have to wrap it up there. We're now out of time. As I indicated earlier, this session will be archived in about 24 hours, and once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank our presenter today for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. And we hope you found today's event valuable and will return for future IEEE Spectrum webcasts. Thank you.
Thank you very much, Dexter.